March 18th, 1945. 50 miles off the coast of Kyushu, Japan. The morning watch aboard USS Yorktown had just changed when Seaman First Class Robert McNamara climbed the ladder to his battle station in the starboard 5-inch 38 caliber gun mount. The 20-year-old from Pittsburgh had been in the Navy for 8 months. Before Pearl Harbor, he'd worked in his father's steel mill, mixing alloys for armor plate. Now he operated a naval gun designed to destroy aircraft attacking the carrier. McNamara's gun crew had been scanning the clouded sky for less than 3 minutes when movement caught his eye through a break in the overcast. A single Yokosuka D4Y Judy dive bomber, painted in the mottled green and grey camouflage of the Imperial Japanese Naval Air Service, was dropping through the 2,000-foot ceiling like a falling stone. The aircraft's nose was pointed directly at Yorktown's island superstructure, where the captain and air operations officers directed the carrier's movements. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The gun captain, a 30-year-old chief petty officer from New Orleans named Theodore Boudreaux, grabbed the sound-powered telephone handset and shouted the warning that would alert every gun crew aboard the ship. Target, bearing 015, range 3,000 yards, dive bomber, angle 35 degrees. His words were still coming through the circuit when every 5-inch gun on Yorktown's starboard side began swinging to track the diving Japanese aircraft. The Judy was already committed to its attack dive. The pilot, whose name would never be known to history, whose body would never be recovered from the Pacific, had perhaps 30 seconds from the moment he pushed over into his dive until either impact or death. In that half-minute, he would have to maintain his dive angle despite increasingly intense anti-aircraft fire, release his bomb at the optimal altitude to ensure penetration of the carrier's armored flight deck, and if he survived that long, pull away before crashing into the sea or into the carrier itself. It was what every Japanese naval aviator had trained for in the final desperate year of the war. It was what dozens had died attempting in the preceding months, as the kamikazes began their systematic campaign against American carriers. This pilot, flying alone through hostile skies, representing an empire that had already lost the war but refused to admit it, was making his contribution to a lost cause. McNamara's gun fired first, the 5-inch shell leaving the barrel at 2,800 feet per second with a crack that momentarily deafened everyone on the gun platform. The tracer was visible as a streak of red light arcing toward the bomber. Then every other gun on the starboard side joined in. The 20mm Oerlikon cannons opened up, their barrels spinning as they fired 600 rounds per minute, creating a continuous stream of tracers. The 40mm Bofors quad mounts added their heavier shells, reaching farther, hitting harder, their distinctive thump-thump-thump audible even over the roar of the 5-inch guns. The sky between the carrier and the diving bomber filled with tracers, thousands of rounds converging on a single point in space. The Japanese pilot flew straight into what looked like a solid wall of steel. 20mm rounds began tearing through his wings, shredding the fabric-covered control surfaces that governed his aircraft's flight. A 40mm shell exploded directly against his engine cowling, sending metal fragments tearing through the oil cooler and cutting fuel lines. Black smoke immediately began pouring from the Judy's 9-cylinder radial engine. Standard Japanese doctrine at this point called for the pilot to release his bomb and pull away, aborting the attack to preserve the aircraft and pilot for another attempt. But this pilot, perhaps already wounded by shell fragments that had penetrated his cockpit, perhaps simply determined to complete his mission regardless of the cost, held his dive. The Judy continued its screaming descent toward Yorktown's deck, trailing smoke and losing pieces of its airframe. He was close enough now that McNamara could see individual details. The bomb slung beneath the fuselage, a 500-pound semi-armor-piercing weapon specifically designed to penetrate aircraft carrier decks before detonating inside the hangar. The pilot's face briefly visible behind the canopy glass before smoke obscured it. The rising sun insignia on the wings, those red circles that had terrified American forces in 1942, but now seemed merely defiant. The damage to the aircraft becoming more apparent with each passing second as more shells found their mark. At 400 feet altitude, With flames now engulfing his cockpit and his controls essentially shot away, the Judy finally released its bomb. The weapon separated cleanly from its rack, tumbled through the air for half a second as aerodynamic forces stabilized it, then began its ballistic descent toward Yorktown's flight deck. Men on the deck below, who had been watching the entire engagement unfold above them with that peculiar helplessness of those who can do nothing but wait, now braced for impact. Damage control parties grabbed fire hoses and moved toward likely impact points. Medical corpsmen prepared to rush forward to treat casualties. The bomb missed. It fell past the starboard edge of the flight deck, missing the carrier's side by perhaps 15 feet, and splashed into the Pacific without detonating. A dud, or simply a weapon that struck water at the wrong angle for its fuse to function. The Judy, now nothing more than a flaming meteor trailing pieces of wing and fuselage, passed directly over the flight deck near the island. Men on the gun platforms could feel the heat radiating from the burning aircraft, could smell burning oil and fabric, and the acrid stench of spent explosives. The bomber crashed into the sea 50 yards off the port side, sending up a geyser of white water that rose higher than the carrier's radar masts before collapsing back into the ocean. Yorktown sailed on, untouched. Her massive bronze propellers continued turning, driving her through the Pacific swells at 25 knots. Her 8 Babcock and Wilcox boilers continued generating steam. Her anti-aircraft guns fell silent, their crews already reloading and scanning the sky for the next threat. Her crew breathed again, that peculiar collective exhalation that follows moments of extreme tension when death has passed close enough to feel. In Combat Information Center, deep in the ship's hull, protected by layers of special treatment steel that would become crucial to this story, officers marked the engagement in the war diary. 1 enemy aircraft destroyed by anti-aircraft fire. No damage to own ship. No personnel casualties. The entry took less than a minute to write, just another routine notation in a war diary already filled with similar entries from months of combat. But what the diary didn't record, what couldn't be recorded in the sparse military prose of official documentation, was that this near miss represented something far more significant than simple luck or good gunnery. The carrier beneath these men's feet had been built according to principles that military experts worldwide had declared economically impossible just 5 years earlier. Her survival over the next months of the most intense naval combat in human history would validate a metallurgical revolution that began not in a shipyard, not in a naval architect's office, but in a Pennsylvania steel mill 35 years earlier, where men in laboratories were trying to solve a problem that seemed to have no solution. The story of how USS Yorktown became nearly unsinkable, of how she would survive attacks that sank other carriers, of how the metal in her bones would prove more important than the courage of her crew, starts in 1910 in an experimental metallurgy laboratory at Carnegie Steel Company's Edgar Thomson Works in Braddock, Pennsylvania. The facility, named after Andrew Carnegie's mentor and first business partner, sat on the banks of the Monongahela River just outside Pittsburgh. It was the heart of American steel production, where the raw iron ore from Minnesota's Mesabi Range was transformed into the structural steel that built skyscrapers, bridges, battleships, and the industrial infrastructure of early 20th century America. Here, in laboratories that most Americans never knew existed, metallurgists worked on problems that industrial America desperately needed solved. One of those problems had haunted naval architects since ironclad warships first appeared during the American Civil War 50 years earlier. The problem was elegantly simple to state, but seemingly impossible to solve. Armor plate was deadweight. It protected ships from enemy fire, certainly, and that protection was valuable, even essential. But armor contributed absolutely nothing to the structural strength of the vessel. Every pound of armor had to be supported by structural steel beneath it. Every ton of armor plating on a ship's belt or turret or deck was pressing down on frames and beams and keel members that could have been lighter and the ship faster if the armor wasn't there. A battleship of the era might carry 3,000 tons of armor distributed across its belt, turrets, conning tower, and protective decks. That entire mass of steel served only one purpose: protection, while contributing nothing to holding the ship together, to resisting the stresses of waves and weather, to bearing the loads of the ship's machinery and armament. The armor itself couldn't help support the ship's structure. Face-hardened armor plate, specifically developed to shatter incoming armor-piercing shells, was far too brittle to serve as structure. It would crack under the continuous flexing stresses that ships experienced in heavy seas as their hulls worked and twisted through the waves. The lead metallurgist working on this problem was a Carnegie Steel engineer, variously identified in different sources as Howard Scott, though some company records suggest the development team included several researchers whose individual contributions later became merged in institutional memory. What's certain from the documentary record is that someone at Carnegie Steel recognized a fundamental opportunity that others had missed. If you could develop an alloy steel that was both protective like armor and ductile like structural steel, possessing the hardness to resist penetration and the toughness to absorb flexing loads, and that metal could simultaneously protect the ship and hold it together, every plate would serve two purposes instead of one. The technical challenge seemed insurmountable to most metallurgists of the era. The properties they were seeking appeared to be mutually exclusive, contradictory requirements that couldn't coexist in the same material. Armor steel had to be extremely hard to resist penetration by armor-piercing projectiles and to prevent fragmentation when struck by shell splinters or bomb fragments. That hardness came from high carbon content and careful heat treatment through a process called carburization, which made the steel surface as hard as glass, capable of shattering incoming projectiles. But that very hardness also made the steel brittle and prone to catastrophic failure under shock loads. Structural steel, by complete contrast, had to be ductile enough to bend without breaking, to absorb shock loads through elastic deformation, to flex with the ship's hull as it moved through waves without developing cracks or fractures. That ductility required much lower carbon content and entirely different heat treatment processes, which made the steel relatively soft and easily penetrated by projectiles. The two properties, hardness and ductility, appeared to be opposite ends of a spectrum where you could have one or the other, but never both. Metallurgy textbooks of the era explicitly taught this principle. Students learned that increasing hardness inevitably decreased ductility and vice versa. But Carnegie's researchers, working in their Pittsburgh laboratories with access to the most advanced metallurgical equipment available in America, weren't constrained by textbook limitations. They were experimenting with nickel-chromium alloys, systematically testing different percentages and combinations, trying various heat treatment processes, searching for a composition that would somehow bridge the unbridgeable gap between armor hardness and structural ductility. The breakthrough came sometime around 1913, though exact dates are difficult to establish because Carnegie Steel, like all commercial enterprises of the era, kept its metallurgical developments secret for competitive reasons. The alloy they developed contained approximately 3.5% nickel by weight, 2% chromium, and 0.4% carbon. The specific percentages varied slightly depending on the intended thickness of the plate, with thicker plates requiring slight adjustments to ensure proper heat treatment throughout the material's depth. Initially, the Carnegie researchers also experimented with adding small amounts of vanadium, a relatively expensive alloying element that showed promise in early tests. But vanadium was dropped from the formula after 1914, when they discovered it wasn't actually necessary to achieve the desired properties and only added to manufacturing costs. The final composition was remarkably simple by later standards, just nickel, chromium, carbon, and iron, with the usual small amounts of manganese and silicon that were present in all steel. The nickel provided toughness and prevented the steel from becoming too brittle during the hardening process. Nickel steel had been known since the 1880s, but earlier formulations used much higher nickel percentages. The Carnegie researchers discovered that a relatively modest nickel content, when combined with chromium, produced better results. The chromium contributed to wear resistance, helped maintain hardness without requiring excessive carbon, and most importantly, improved the steel's resistance to corrosion. The carbon content was carefully balanced at a level high enough to allow effective hardening through heat treatment, but low enough to maintain some degree of ductility in the finished product. Carnegie Steel began producing test plates in thicknesses ranging from 0.5 inch to 4 inches, which covered most naval armor applications, except for the thickest battleship belt armor and turret faces. The material showed remarkable and unprecedented properties. When properly heat-treated through a carefully controlled heating and cooling process, it resisted fragmentation as effectively as face-hardened armor plate for all thicknesses below 4 inches. Small arms fire couldn't penetrate it. Artillery shell splinters bounced off or shattered against its surface. Bomb fragments that would tear through mild structural steel like paper barely scratched this new material. But unlike traditional armor plate, which was essentially dead weight that had to be supported by the ship's structure, this new steel could be welded without losing its protective properties. That was revolutionary. Traditional armor plate couldn't be welded because the extreme heat of welding destroyed the carefully controlled grain structure that gave the armor its hardness. Armor plates had to be bolted to the ship's structure, which added weight and created potential weak points. This new steel could be welded directly into the ship's framework using standard arc welding techniques, though the welding process required some special procedures. The new steel could also be cold-formed into curves using hydraulic presses, allowing it to follow the complex shapes of a ship's hull. Traditional armor plate couldn't be bent without cracking. This new steel could be drilled and machined with standard cutting tools, though it wore tools faster than mild steel. It required harder drill bits and slower cutting speeds, but it could be worked in any shipyard without requiring special equipment. Most remarkably, it maintained structural load-bearing capacity equivalent to high-tensile structural steel, with a yield strength around 40,000 pounds per square inch. That meant the armor could be incorporated into a ship's framework as load-bearing structure rather than as deadweight. A deck plate made from this material would simultaneously serve as the ship's main strength deck, bearing the structural loads of the superstructure and machinery above, while also providing armor protection against bombs and shell fire from above. A bulkhead made from this material would help maintain the ship's longitudinal strength while also protecting against fragmentation and helping contain fires and flooding. Naval Ordnance Officers at the Navy's Bureau of Construction and Repair, the organization responsible for warship design before it was reorganized as the Bureau of Ships in 1940, took immediate notice of these developments. They recognized that this new material could fundamentally change how warships were designed and built. They conducted exhaustive ballistic testing at the Navy's proving grounds in Dahlgren, Virginia, a facility specifically established for testing armor plate and naval ordnance. The tests were methodical and comprehensive. They fired armor-piercing shells at sample plates from various ranges and impact angles, measuring penetration depth and backface deformation. They detonated explosive charges against the steel to test its resistance to fragmentation, measuring how far fragments traveled and how much energy they retained. They subjected sample plates to stress tests that simulated the flexing loads a ship's structure experiences in heavy seas, applying millions of cycles of stress to see if fatigue cracks would develop. They tested welded joints to verify that the welding process didn't create weak points in the material. The results exceeded the Navy's most optimistic expectations. For horizontal armor applications like protective decks, for bulkhead applications where internal subdivision was needed, for any armor requirement where thickness was typically below 4 inches, this new steel performed as well as or better than traditional face-hardened armor while weighing significantly less and contributing to structural strength rather than being deadweight. The implications for warship design were profound and immediately obvious to naval architects who understood the significance. The Navy's Bureau of Construction and Repair formally designated the new material Special Treatment Steel, immediately adopting the abbreviation STS that would appear in thousands of construction specifications and design documents over the next 50 years. By 1915, detailed specifications for STS had been written into Navy construction standards, and the material was approved for use in all new warship construction. The specifications covered the exact chemical composition, the heat treatment processes required, the mechanical properties that finished plates had to achieve, and the welding procedures that had to be followed. But there was a significant problem that would limit STS use for the next 25 years. Special treatment steel cost approximately 30% more than mild structural steel. For large warships using thousands of tons of steel in their construction, That cost difference translated into millions of dollars per ship. A battleship that might use 10,000 tons of steel in its structure would cost $3 million additional if built entirely from STS rather than in conventional mild steel and armor plate combinations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Navy, operating under peacetime budgets that were always tight, couldn't justify that expense for every application. So they used STS selectively, primarily for protective deck armor, where its dual properties as both armor and structure provided the most value, and for critical internal bulkheads, where splinter protection and structural strength were both important. But hull plating, most internal framing, and the majority of structural members continued to be built from cheaper, mild structural steel. This selective, economical approach characterized American naval construction throughout the 1920s and 1930s. During this period, American battleships and cruisers used STS for their main protective decks and for critical bulkheads around magazines and machinery spaces, but the bulk of their structure remained conventional mild steel. The three aircraft carriers built during the 1920s, Lexington and Saratoga, converted from battlecruiser hulls, and Ranger, the Navy's first purpose-built carrier, used even less STS than battleships because the Washington Naval Treaty limitations on carrier displacement forced designers to minimize weight wherever possible. When the Yorktown-class carriers were designed in the mid-1930s, representing the Navy's most modern thinking about carrier architecture, they still used STS sparingly. Their hangar decks, where aircraft were stored and maintained, were constructed from mild steel rather than armor plate. Their internal bulkheads were minimally armored. Their flight decks consisted of thin, wooden planking over mild steel plating that provided no meaningful protection against bombs. The ships were fast, capable of operating large air groups, but they were fragile by design because treaty limitations left no displacement available for protection. The naval architect who would completely change this conservative, cost-conscious approach to carrier design was Homer Lenoir Ferguson, though he wouldn't get his opportunity to revolutionize carrier construction until the Washington Naval Treaty limitations were finally lifted in 1937, when Japan formally withdrew from the treaty system. Ferguson's path to revolutionizing carrier design began far from any ocean, in the mountains of western North Carolina, where he was born in Waynesville on March 6, 1873. His father, William Burder Ferguson, was a Confederate veteran who had fought through the entire Civil War, surviving battles that killed many of his comrades, and returned home to build a successful law practice in the post-war South. William Ferguson raised his 5 children, 3 sons and 2 daughters, with the strict Scotch-Irish Presbyterian discipline that characterized that time and place, a discipline that emphasized hard work, personal responsibility, rigorous education, and an almost religious devotion to doing any task correctly rather than merely adequately. At age 15, remarkably young, even for an era when most people completed their formal education much earlier than today, Homer Ferguson entered the United States Naval Academy at Annapolis, Maryland. Family accounts differ on exactly how this came about. Some sources suggest he took the entrance examination on a dare from a cousin who was also applying. Other accounts indicate that his father, recognizing Homer's exceptional mathematical aptitude and his fascination with how things worked mechanically, actively encouraged him to seek appointment to the academy. Regardless of the exact circumstances, young Ferguson passed the entrance examination with high marks and received his congressional appointment. He entered the academy in 1888 and graduated 4 years later in 1892. His exact class standing is unclear from surviving records, with some accounts placing him first in his class, while others suggest he graduated third. What all sources agree on is that he graduated with honors, demonstrating exceptional ability in mathematics, mechanical engineering, and naval architecture. His academic performance was strong enough that the Navy, recognizing his potential, made an unusual decision that would shape not just Ferguson's career, but ultimately the design of every American aircraft carrier built in the next 50 years. Instead of assigning Ferguson to sea duty aboard a warship like most newly commissioned ensigns, which was the standard career path for Naval Academy graduates, The Navy sent him to Glasgow University in Scotland for 3 years of advanced study in naval architecture and marine engineering. From 1892 to 1895, Ferguson studied under Scottish professors, who were then acknowledged worldwide as the leading authorities on ship design and construction. This wasn't merely advanced education. It was an immersion in a completely different philosophy of how ships should be conceived and built. Glasgow in the 1890s was unquestionably the centre of global shipbuilding. The River Clyde shipyards built more tonnage than any other location on Earth. Scottish yards were famous for building the fastest, most technically innovative vessels afloat. They had pioneered the use of iron in ship construction when everyone else was still building with wood. They had developed and perfected the marine steam turbine that would revolutionize naval propulsion. Most famously for American history, Scottish yards had designed and built the Confederate blockade runners during the American Civil War, vessels so fast and maneuverable that Union Navy ships could rarely catch them despite overwhelming numerical superiority. Ferguson absorbed far more than just technical knowledge during those 3 years in Scotland. He internalized the fundamental Scottish philosophy about ship design that his professors taught. That philosophy, stated clearly and repeated constantly, was brutally simple. Ships should be built to survive first, to perform second. A ship that sinks cannot complete its mission no matter how fast it is or how heavily armed. Therefore, survivability must be the absolute foundation of every design decision, the requirement that takes precedence over everything else. Speed, armament, aircraft capacity, all of those come second to the fundamental requirement that the ship must be able to take damage and continue fighting. This philosophy was actually contrary to much American naval thinking of the late 19th century, which tended to emphasize offensive power and speed over defensive protection. American naval officers, influenced by the theories of Alfred Thayer Mahan about the decisive battle and the importance of concentrating maximum offensive power, often viewed armour as deadweight that slowed ships and reduced their striking power. But Ferguson's Scottish professors had seen too many ships sink from damage that better construction could have survived. They taught him that the ship that survives the battle wins the battle, regardless of how that survival is achieved. Ferguson returned to the United States in 1895, carrying this conviction deep in his professional consciousness, a conviction that would shape his entire career and ultimately save thousands of American lives. He spent the next decade serving as a naval constructor, the specialized engineering officer responsible for overseeing warship construction and repair. He moved between various shipyards and Navy facilities as assignments rotated. He inspected construction at the Bath Iron Works in Bath, Maine, one of America's premier shipyards. He oversaw building projects at the Navy yards in Bremerton, Washington, and Portland, Oregon. He supervised battleship construction at multiple East Coast facilities. He was, by all accounts and fitness reports, extraordinarily good at his job. His reports were detailed, insightful, demonstrating deep understanding of both the theoretical principles and the practical realities of ship construction. His recommendations consistently improved construction methods and solved problems that had stymied other engineers. His designs, when he was given the opportunity to create them, worked exactly as intended. But despite his exceptional abilities and consistent excellent performance, Ferguson grew increasingly frustrated with the Navy's bureaucracy and its glacially slow promotion system. He watched as officers with less technical ability, less dedication, and fewer accomplishments received promotions while his own advancement stalled. The Navy's promotion system of that era relied heavily on seniority and political connections rather than merit. Ferguson had the merit but lacked the connections. His frustration finally reached a breaking point in 1905. At age 32, having served in the Navy for 13 years since his academy graduation, Ferguson resigned his commission and accepted a civilian position at Newport News Shipbuilding and Dry Dock Company in Newport News, Virginia. The position was Assistant Superintendent of Hull Construction, a senior engineering role overseeing the actual building of ship hulls. The annual salary was $7,500, which was substantially more than his Navy pay as a lieutenant. Ferguson also successfully negotiated a $5,000 signing bonus, which he immediately and characteristically used to build a house in Newport News for his growing family rather than spending it on personal luxuries. At Newport News Shipbuilding, Ferguson's career accelerated with remarkable speed. His abilities, which had been somewhat constrained in the Navy's rigid hierarchy, found full expression in the more meritocratic environment of private industry. He became superintendent of all hull construction within 2 years, demonstrating his ability to manage hundreds of workers and coordinate complex construction projects. He was promoted to general manager soon after, responsible for the entire shipyard's operations. By 1912, he had become vice president of the company, the number 2 executive position. The shipyard's owner, railroad magnate Collis Potter Huntington, had established the facility in 1886 with a business philosophy that aligned perfectly with Ferguson's own values and the lessons his Scottish professors had taught him. Huntington had famously declared his intention in plain language that became the shipyard's unofficial motto: "We shall build good ships here," he said. "At a profit if we can, at a loss if we must, but always good ships." Quality and integrity were not negotiable. Profit was desirable but secondary to reputation. On May 7, 1915, a tragic event thrust Ferguson into the leadership position he had been preparing for his entire career, though under circumstances he never would have chosen. The shipyard's president, Albert Lloyd Hopkins, was travelling to England aboard the British ocean liner RMS Lusitania on company business, planning to negotiate contracts with British shipyards and discuss technical matters with Royal Navy officials. The Lusitania was torpedoed without warning by the German submarine U-20 off the Irish coast. The liner sank in just 18 minutes. Hopkins died when the ship went down, one of nearly 1,200 victims, including 128 Americans, in an attack that helped push the United States toward entering World War I. 69 days after Hopkins died, on July 22, 1915, the company's board of directors met in New York and unanimously elected Homer Ferguson as the new president of Newport News Shipbuilding. He was 42 years old. He would hold that position, leading the company through challenges that would have broken most men for the next 31 years. His tenure would span World War I, where the shipyard built dozens of destroyers for the war effort. It would span the disarmament treaties of the 1920s that cancelled nearly all warship orders and nearly bankrupted the company. It would span the Great Depression, where private shipyard work dried up almost completely. And it would span World War II, where the shipyard would build some of the most important warships in American history. Under Ferguson's leadership, which combined technical brilliance with genuine concern for his workforce, Newport News became widely recognized as the premier naval shipbuilder in the United States. He established the Apprentice School in 1919, creating a comprehensive 4-year training program that would produce the skilled machinists, welders, electricians, and other craftsmen the yard would need for future projects. The school still operates today, training each generation of shipbuilders in the traditional crafts while incorporating modern technology. He convinced the federal government during World War I to fund construction of Hilton Village, one of America's first comprehensively planned worker housing communities, to address the chronic shortage of affordable, decent housing near the shipyard. The village, designed by prominent architects and featuring then innovative urban planning concepts, provided hundreds of comfortable homes for shipyard families. After the war, when the government wanted to sell the properties, Ferguson worked with industrialist Henry Huntington, son of the shipyard's founder, to facilitate sales to the workers themselves, turning renters into homeowners. During the desperately lean years of the 1920s, when the Washington Naval Treaty's limitations on warship construction cancelled virtually all naval orders and dozens of American shipyards went bankrupt and closed forever, Ferguson kept Newport News alive through sheer determination and willingness to take any work, regardless of profitability. The shipyard fabricated railroad freight cars, built highway bridges, manufactured street signs and traffic lights, produced massive turbines for hydroelectric dams, and took dozens of other jobs that had nothing to do with shipbuilding. Most famously, Ferguson accepted a contract to renovate a seized German ocean liner, the Vaterland, converting her into the American passenger liner Leviathan. Ferguson deliberately bid $1.2 million below the actual cost of the work, because keeping his workforce employed and his facilities operational was more important than short-term profit. He understood, with strategic vision that few businessmen possessed, that the skilled workforce he had assembled couldn't be recreated easily. If those workers scattered to other industries, that accumulated skill and experience would be lost forever. When naval contracts eventually resumed, and Ferguson believed they would despite the current disarmament treaties, the yard needed to have its workforce intact and ready. His strategy proved brilliant. By the mid-1930s, as war clouds gathered over Europe with Hitler's rise to power in Germany and gathered over Asia with Japan's invasion of China, the United States Navy began planning a major expansion of its fleet. The Washington Naval Treaty, which had limited naval construction since 1922, was set to expire. Japan had already given notice of withdrawal. Italy was openly defying the treaty. It was clear that a new naval arms race was beginning and America needed to be ready. The Navy began planning a new generation of aircraft carriers to replace the treaty-limited designs of the 1920s and early 1930s. These new carriers would form the backbone of American naval aviation for the foreseeable future. The result of this planning process would be designated the Essex class, and Homer Ferguson, president of the shipyard that would build more of these carriers than any other facility, would have his once-in-a-lifetime opportunity to apply everything he had learned over 45 years of studying, building, and thinking about ships. The Bureau of Ships, which had replaced the old Bureau of Construction and Repair in June 1940, held a series of design conferences throughout 1938 and 1939 to determine the characteristics of the new carrier class. Ferguson attended these conferences as Newport News' representative, since his yard would almost certainly be selected as one of the lead builders for any new carrier program. The facility's reputation, its experienced workforce, and its track record of delivering quality ships on schedule made it the obvious choice. Ferguson listened carefully as Navy officers and civilian naval architects debated and discussed the proposed specifications. They argued about carrier displacement, which directly determined how large the ship could be. They debated aircraft capacity, with some officers pushing for the ability to carry and operate 100 aircraft, the famous Sunday punch concept that would supposedly deliver decisive blows against enemy fleets. They discussed speed requirements, with 33 knots considered necessary to keep pace with fast battleships. They examined armament specifications, determining how many anti-aircraft guns would be needed to defend against air attack. All of these were standard naval architecture considerations, the normal debates that accompanied any major warship design. But Ferguson, drawing on his education in Scotland, his decades of experience building ships, and his deep understanding of what happened to ships when they got hit in combat, and was waiting for the right moment to make a radical proposal that he knew would meet fierce resistance. When the discussion finally turned to protective features and armor distribution, Ferguson made his move. He proposed building the entire carrier structure from special treatment, steel, not just selected portions, not just the most critical areas, the entire structure. The hangar deck, where aircraft were stored and maintained between flights, would be 2.5 inches of solid STS, rather than mild steel. The fourth deck, forming the bottom of the hangar box and separating the hangar from the machinery spaces below, would be 1.5 inches of STS. Interior bulkheads throughout the ship, the walls that subdivided the vessel into hundreds of separate compartments, would be STS, wherever structurally and economically feasible. The armor belt at the waterline, protecting against shell fire and torpedo hits, would use 4 inches of traditional Class B armor plate backed by additional STS plating that would serve as both backing structure and additional protection. The suggestion seemed economically absurd to many of the officers and engineers present at the conference. Previous carrier designs, including the recently completed Yorktown class, had used STS selectively and sparingly for critical areas like certain bulkheads and portions of the protective deck. Ferguson was proposing to use this expensive material everywhere, in quantities measured in thousands of tons per ship rather than hundreds. The immediate objection focused on cost. Bureau of Ships cost analysts, working with procurement specialists who understood steel pricing, calculated the financial implications of Ferguson's proposal with brutal clarity. An Essex-class carrier built using Ferguson's extensive STS construction philosophy would cost approximately $5 million more than a carrier built using conventional structural steel with selective armor plate. That was an enormous sum in 1939 dollars, when $5 million could build an entire destroyer with money left over. And the Navy was planning to build multiple carriers of this class, potentially 20 or more over the next decade. If they built 24 ships using Ferguson's proposal, that was $120 million in additional construction costs, just for the more expensive steel. The Bureau of Ships officers, operating under strict budget constraints imposed by Congress and facing pressure to maximize the number of ships built within available appropriations, initially rejected Ferguson's proposal outright as economically unfeasible. The Navy simply couldn't afford to spend that much extra money on protective steel when those funds could instead be used to build additional ships. Quantity had its own quality, several officers argued. Better to have more ships with adequate protection than fewer ships with exceptional protection. But Ferguson was not a man who accepted defeat easily, especially when he believed he was correct on both technical and moral grounds. He requested a special meeting with the Secretary of the Navy and the Chief of Naval Operations, bypassing the normal bureaucratic channels. Such a request from a civilian shipyard executive was highly unusual, but Ferguson's reputation and the importance of the carrier program ensured that the meeting was granted. In that meeting, which took place in Washington in early 1940, Ferguson laid out his argument with the precision of an engineer and the passion of someone who understood that his decisions would directly determine whether sailors lived or died in the coming war that everyone knew was approaching. His opening statement was characteristically direct and would become famous within Newport News shipbuilding, repeated to generations of apprentices as an example of speaking truth to power. "You're not paying for steel," Ferguson told the Secretary and the Chief of Naval Operations. "You're paying for men to go home alive. That's what this decision is really about. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe."